Okay, so welcome back. Let's start the second talk of the morning session. It's my great pleasure to introduce Michael Robinson from our neighborly American University, located close by. And today he's going to talk about the topology of circular synthetic aperture sonar and implications for classification.
Great, thank you.
Yours, thank you.
Thank you, and welcome everyone. Thanks for coming into the second session today of the fall rather than February Fourier talks. Great to see everyone in person here and everyone online as well. So keeping the theme of remote sensing, I'm going to talk about sonar rather than radar, but actually everything that I'm going to say applies equally well in sonar and radar just the same. A few acknowledgements before we get started. This is funded by the Office of Naval Research. A number of people involved over the years, including now Dr. Michael Rawson, who is along with us again today. So I'm going to talk about circular aperture sonar, in which I mean that you've got a target kind of in the middle and you have a sensor that goes around the target, makes an orbit around the target, getting back to the place where it started. And one of the things that I've often thought about is sonars that are, let's just say, budget sonars, i.e. those that are not particularly well calibrated, those that are not particularly well understood in terms of their trajectory. The trajectory, if it goes around the target, might not be a perfect circle. Well, what do you do in that case? Well, there are, of course, standard algorithms for correcting this kind of problem, and they work up to a point. If you have a really big distortion, they don't work as well. And so the question is, well, can you still use them? Maybe you can, maybe you can't. So this talk is about what can you still see? So the general idea is traditionally what people do with a radar or a sonar when they take a sonar system is they try to form an image. They make a picture of the target so that you can look at it and see what it is. That seems natural enough. It's a very standard thing that people do. And the focus for today is not forming images, because if you distort the trajectory substantially, well, you really can't form a good image. So typically what you'll see is instead of an image, you'll see the raw data. And just to give you an idea, as you go around the target, the vertical axis in all of my plots will be the look angle, or something that's kind of a proxy for the look angle. If you will, the slow time in the two-time setup of slow time being your trajectory, fast time being within a pulse. And for instance, you might look at the pulse frequency. That's the horizontal axis. If you take a look at this, the standard thing that one does is one does an integral transform to turn this into an image. So typically you end up with a picture that if you started out with a target that had 3 point scatterers in it, the image you form will have 3 dots, more or less. Sounds standard enough. And that works pretty well if you know the trajectory. And part of the reason for doing the image formation idea is that humans like looking at pictures. If you look at a picture and it looks like a car, it's probably a car. Sounds good. Of course, if you look at a sonar image, the bandwidth and the wavelength associated with sonar tends to be different from optics. So the images don't look like normal images, but that's okay. You can train yourself, or you could train an algorithm to classify based on the image that you're looking at. Now, if you do, as I said, that I'm interested in is when there's a lot of distortion in the trajectory, it becomes harder to form the image. The images get blurred and distorted. If you want to train on that, train a classifier, say either a human or a machine learning classifier, you need to parameterize all these different possibilities, generate lots and lots of data that picks up each of these distortions. Of course, lots of people have done this sort of thing. I've done this sort of thing to train classifiers, and that all seems reasonable, but you might ask, is this like overkill? Do we really need to do this much reparameterization data generation in order to train an algorithm? Or is there simply less data available to classify on when you have these kind of distortions? Well, so my real question is, what relevant information is still there if you allow severe distortions? And by severe, I'm going to put on my differential topologist hat and say any smooth function can distort my trajectory. That's pretty severe. I'm not likely to be able to algorithmically autofocus my way out of this problem. So we need some kind of less rigid signal model. Okay, so let's take a step back and ask, what do people normally do when they classify? Well, normally you've got some kind of structure, some sensor configuration, which has information about what the trajectory looks like, maybe a radius and an angle, perhaps even an angular function to tell me how I'm going around the target, as well as other parameters for the sensor, its bandwidth, waveform. We heard lots about waveform design just a few moments ago. All of that information is kind of baked into some kind of general configuration of the sensor. Think of that as a point in some high dimensional space. And you'll take some measurements. Those measurements might be real if you're doing optics. They might be complex if you're doing radar or sonar. As far as, again, topology hat on, complex equals real with twice the dimension. Don't really care. Not going to do anything particularly algebraic. So I end up collecting, say, a data set, and I want to compare it to some other archived data to say, well, have I seen something like this before? And if they're similar, how similar are they? I end up effectively with two functions I need to compare, a function from the space of sensor configurations to the space of measurements. Okay, that works very well if I have good control of the sensor configuration. If I don't have good control of the sensors, well, then these configuration spaces may be vastly different. And so it's very hard to compare these two functions because although the ranges are the same, the codomains are the same, the domains are not. What do I do? Well, that's a real problem. Well, one idea is to say, well, let me just look at the images. If I just look at the images of these two functions, I now have data that live in the same space. And in fact, this is something that people who study topological data analysis have been thinking about. Think of the image of your sensor configuration, i.e. the raw data in some high dimensional space. Think of it as a finite metric space, finite because you've collected finite samples, and ask how far apart are those in some reasonable sense. Okay, that seems reasonable enough given the fact that we don't have control on the sensors. And in fact, the standard topological data analysis workflow using persistent homology effectively ignores the sensor configuration spaces altogether. Now, this might seem like this is, well, first idea of trying to parameterize everything was overkill. Maybe this is underkill. But in fact, it does tend to work in practice. You can actually do reasonable classification using topological data analysis, which kind of begs the question, well, when does it break? How badly can I screw up the sensor configurations and still get good results? So I prefaced the title of this talk as being for circular aperture sonar, which means to me that I have some knowledge of the sensor configuration spaces. It's just that there may be a distortion. So effectively, what people normally do is they take the sensor configurations, they try to say, well, okay, the slow time wasn't really good, the trajectory was not really good, but I got back to the same place. So I have this smooth function distortion in there. So what I want to do is I want to refer back to some kind of idealized reference space, actually say look angle. If I can refer back to that look angle by some kind of procedure, then I can say, all right, I'm going to now compare from the same space. Now, this reference space is perhaps idealized. If there's not too much distortion, I can actually find it using something like autofocus. But if it's really, really messed up, there's no hope, right? Well, actually, look at this. This is a function, smooth function, smooth function, smooth function. I'm really actually interested in understanding what the possible factorizations of this smooth function into another pair of smooth functions looks like, given the fact that I know what the reference space is. So the high level insight that I want to bring to bear to this problem is if I have some idea what the reference space is, say if I'm dealing with a circular synthetic aperture system, I know the reference space ought to actually be a nice circle of some sort. So if I can ask, what do all the factorizations of my data through this circle, what do those look like? Then that could tell me something about the kinds of target classes that might be present in my data. Okay, so effectively, this will allow me to ignore the sensor behavior because I've kind of factored it out in some precise but weird sense, and focus just on the effects of the target on its factorizations. Okay. Now, I'm very much someone who likes to play with some real data when I get my hands on it. And as I said, I like to work with budget systems. So this is actually data collected from a sonar system that I threw together from a cell phone, in fact, and imaged a ceiling fan that was rotating. So this is actually not a circular synthetic aperture sonar. Technically, it's a circular inverse synthetic aperture sonar. All right, whatever. Again, topologist hat on, don't care. Point of the matter is, though, I collect some pulses. I get a time series, organize those pulses. So I have something like a slow time. Well, actually, I transpose the slow time versus fast time plot. And if I look at the image of this in high dimensional space, I end up with some kind of circular structure on the bottom right of the slide. This is indicating that that reference space that this orbiting is probably indeed a circle. And you can ask the question, how do these data, how does this function from time to this image factor through? And as a topologist, you'll say, gosh, there's a winding number in there. I can see the fact that this is counting how many times I've gone around. And in fact, if I ask how many times does this go around, it turns out that it happened to be 4 times the number of rotations that the ceiling fan made. Why 4 times? Oh, because the ceiling fan had 4 blades. Interesting. Okay, so this suggests that there's some merit to this idea. Let me also point out that even if you have severe distortions, this image of your data is actually somewhat preserved. So I have, now these are simulated results, 2 simulations of a 3-point scatterer target. Very simple, just so I can get it on the screen. This works with higher dimensional things, but the spaces look messier. Vertical axis on both these top plots are the look angle, and this is the absolute actual look angle. The horizontal axes are the fast frequency, so frequency within each pulse. Each row is a pulse. And what I've done for you is I've formed up images using time domain back projection, which is my favorite technique for this sort of thing. And you can see on the left, with no distortions, that you get a nice focused image. On the right, you get a blurred image because the trajectory is not what I said it was. But if you look at the image, the space of pulses, they look pretty similar. In fact, really the only difference turns out to be that there's a little bit of sampling error. So again, this suggests that this topology of the space of echoes has something to do with the structure of the target without paying attention to the trajectory. So the sensor structure, which definitely messes up the image formation, doesn't change the topology. Okay, well, let's try to play on that a little more deeply. Saying this sort of the same thing again, if you start out orbiting your target, getting back to the target somehow in slow time, if you could find a way to refer the trajectory to this idealized but otherwise inaccessible look angle, which is on the circle, nice and rigid, actually matches up with geometry, that would then give you an idealized model of the target. But of course, we've got some collected data that don't really agree with that, and we don't know what the factorization is. But we can ask, what do the factorizations look like? And how many are there, and how are they structured? Because effectively, you want to classify over here, where you've got the idealized. Okay. Now, one of the interesting things that comes out of this is, again, if I'm saying we're in circular synthetic aperture sonar, the reason why I'm saying that is because it limits the dimension of the topology. The spaces are lower dimensional. They're all one-dimensional manifolds. And so I can actually prove some things about it. In fact, if you look at the structure of these maps, under the assumption that your sensor doesn't stop at any point, which for the most part is good. The trajectory may be terrible, but it probably doesn't stop if you're moving. If that's the case, then in fact, these images that you get, we saw some circles before, that's actually a special case. In general, you end up, it's called a wedge product of circles and intervals, i.e. you take these circles and stick them together at a common point. And actually, it turns out that this really relates to the physical acoustics that are involved. The point that they all get stuck to actually tends to, when you look at the data, to kind of be a little bit hazy because there's some noise. That little hazy dense point is the areas where there are low signal, places where you're sitting inside a null in the sonar cross section. And then each time you get some kind of bright, specular, or otherwise prominent reflection, you make an excursion out from that center point and come back. The reason why you end up with lots of circly things is because we're in a circular synthetic aperture sonar. Eventually, you get back to where you started. But sometimes these two little filaments that would be sort of out and back might be pretty much straight out and straight back if there's a symmetry in the target. So the geometry of the target impacts the topology of the space of echoes that you see. And so you can sort of pick apart the structure of the target, asking the question, how many different kinds of strong prominent scatterers are present in that target that can be read off of the structure of the space of echoes. And this theorem is true regardless of what this trajectory function looks like. So what this means is, in general, if I don't know the trajectory function, don't have any control on it because I'm sloshing around, you basically can classify on 4 different kinds of things. The number of prominent scatterers, their sonar cross-section, how bright they are, how reflective they are, their effective beam width as you move around, that tells you kind of how broad these circles are, and the order in which they occur, as in which order do you traverse them as you move around the target. This is pretty much all you can tell. What this means is, even if you were to feed a machine learning algorithm lots of data from a circular synthetic aperture sonar system that doesn't have good control of the trajectory, this is what it's going to learn, because this is what mathematically is present. So now, of course, you could say, well, if I know something about the trajectory, I could do better. Of course, if you know something about the trajectory, control that trajectory function, then you could do things like image formation and autofocus, and you're in much better shape, and there are more features. Certainly. And fantastic. I'm not. And what this suggests, though, and this is a conjecture, I have not proven this, but it intuitively suggests that the reason why the topological data analysis ideas work, where they produce persistence diagrams for your data, effectively they pick up the first 3. Number of prominent scatterers, their cross-section, and their beam width. It doesn't see the ordering. In fact, the ordering is a subtle relationship between homotopy and homology. Okay, let me actually justify this with some real data. So these are data that were collected from a laboratory sonar system from ARL Penn State University. Their CSAS system. This is a circular synthetic aperture sonar. Again, actually, technically, I think it's an inverse circular synthetic aperture sonar because I think the sensor remained fixed and the target is rotating. Doesn't really matter, again, to me as a mathematician. Let me point out that we've got the kind of target that you might want to look at. In this case here, it's a metal pipe that's placed on this turntable and rotated. This is the raw data from this system on the left. So you have the look angle, again, vertical axis. In this case, this is the true actual measured look angle. And this is a slow time, fast time plot. So the horizontal axis is within range of samples. So each row is a pulse. Now, each row being a pulse translates into a point in the middle plot, which is the space of echoes. This is, of course, if you read, probably can't read it from the back, it's 1,000-dimensional. So I've taken this 1,000-dimensional point cloud, each pulse being a point at a 1,000-dimensional space, and projected it down to 2 dimensions. I could have used something fancier than principal components analysis, but principal components analysis has merit of being easy to interpret. Okay, and certainly quite sufficient. So each point here is a pulse. Okay, and each loop in the principal components analysis plot becomes a point in the persistence diagram, which is computed using persistent homology. So there's a lot of data compression when you go from the left to the right. You started out with pulses and you end up looking at loops in the space of pulses on the right. Okay, so my theorem that I mentioned to you is in fact true. The space in the middle does look kind of like a wedge product of circles and intervals. Indeed it is. Sounds pretty decent. Let's sort of tear this apart physically. So if you look at this particular pipe, you get a rather broad, rather bright specular reflection on the sides of the pipe. Those, in fact, are very visible in the raw data. You can see that there are bright spots there. Those correspond to these big flary loops shooting out from the middle in the from the middle plot in the space of echoes. And in fact, they're quite visible in the persistence diagram as being far away from the diagonal. It's worth noting, even if you know nothing else about topological data analysis, the distance from the diagonal tells you some measure of the significance. In particular, measures the cross-section of this particular target. So that's pretty nice. There's a physical connection between what you see in the persistence diagram and what you see in the space of echoes and what you see in the raw data. There's this nice correspondence and it has a physical acoustic thing. Cool. Okay. In fact, you can also see the creeping wave echoes that run down the length of the pipe as well. They're a bit weaker. You probably see it from the back, but if you were to take a really close look, you can see they're there. They're a little more broad beam width, which also indicates that they're probably going to be a little lower in overall cross section. They kind of get buried in the middle of the space of echoes plot, but actually they're actually visible in the persistence diagram as being one of the off diagonal points. To a different target. This target here has some, rather than specular reflections that were exactly 180 degrees out of phase with each other, now they're a little bit off. Again, however, you can get some big specular reflections off the side of the target. This particular target is a styrofoam cup. Okay, seemed easy enough. They also have Coke bottles and other things, all sorts of random items that they threw into the sonar system to see how it worked. I picked a few of them. So you can see again the very prominent specular reflections. They're visible in all three plots, and in fact, the distance to the diagonal in the persistence diagram correlates very nicely with the sonar cross section of these sides. Awesome. If you look at the top and bottom reflections, they're also present. Again, they're wider beam width, but still there. So the point of the matter is that that this theorem that I mentioned about having your space of echoes being a wedge product of circles and intervals is very much true and very much physically visible. The last sort of point that I want to show you is what happens if you dramatically change the target by popping off the lid on the styrofoam cup. Well, now it's going to kind of have like a horn shape. It'll be kind of echoey. And in fact, that very much happens. You get a nice big echo here. This very complex reflection as you move around. There's a lot of side lobes in the reflective structure. What does that look like in the space of echoes? Well, you get one big, very squirrely loop. Okay, all right. That one big, very squirrely loop is quite visible in the persistence diagram. Is off diagonal. And of course, the natural question is, wait, what happened to all the others? Everything between this plot and this plot, wait, they look totally different. What happened? Well, it turns out that actually did something that I always complain that when my basic stat students do. I changed the axes. There's the actual original plot. It's like really, really teeny in there. Why? Because the echo getting off of the mouth of the cup now opened is really huge. Okay, all right, fair enough. So I'm not lying. It's just sort of weird. Okay, now I've been saying circular synthetic aperture sonar throughout, and that's a very reasonable thing to say. But actually, this idea of exploring the topology of the space of echoes, a way of effectively trying to factor out the different possibilities, works for many other kinds of sonar and many other reflections. So you could do a helical scan, a side scanner, or even I know something about the target and I want to pack that target information in. It turns out that there are lots of different ways you can perform factorizations. Kinds of factorizations that I think are very useful to study are those in which the trajectory function says the sensor doesn't stop. A way to characterize that precisely in a differential topological sense is to say that my trajectory function, here's my domain that I understand, this u is the function I've measured. This trajectory function has to have constant rank, i.e. I can't have any singular points in it, i.e. I don't stop. If I do a helical scan around the target, yeah, I'm not stopping. Sounds pretty reasonable. But if I stop, then you can end up with problems. It's worth noting too, if this guy's got a more or less constant rank, what does that mean? As a smooth function, its derivative, right? Derivative itself is actually approximately constant. That's an extra constraint. Then all of the autofocus ideas. If it's not approximately constant, well, then autofocus fails miserably, and you have to do something like I was just suggesting. It turns out that I don't know what the factorizations are. There are possibly many of them. because, you know, you can probably get the same data various ways, if you will. This is a topological ambiguity. Well, okay, it turns out there's so many of them that they form an entire mathematical category. The objects of this factorizations, and you could have morphisms in this category, are transformations between these different factorizations. An isomorphism on factorization would be to say that, well, okay, fine, like that's like a regular standard radar or sonar ambiguity. Well, that's pretty cool. So a suggestion is that you can use the category itself to identify similar signatures. And effectively what this does, if you use the category as a feature, is it removes the trajectory from consideration at all. Signatures that differ only by trajectory are going to have exactly the same categories. So signatures that differ by more than that, i.e. different targets, will have different categories. That's pretty neat. And furthermore, this category is functorial. It transforms in a reasonable way. Okay, that's cool, except for the fact that it's actually kind of hard to compute. Okay, so I'm not going to compute the sort of general one, but actually, as it turns out, for circular synthetic aperture sonar, the category you want to study actually amounts to characterizing a torus knot. And so in particular, there's a nice theorem that says that if I have a structure, circular synthetic aperture sonar, where I'm factoring through a circle, then in fact, the structure of that category, the isomorphism classes, are in one-to-one correspondence with torus type. That's cool. So let me sort of end with a theoretical example that kind of shows this. Here's a target that consists of 2-point scatterers. The end target consists of the symmetry classes kind of are characterized by the little figures at the bottom. And by looking at what different kinds of factors I have associated with 2 or with 6, those in fact are in one-to-one correspondence with the isomorphism classes of the factors. Well, that's pretty cool. This says then that if I distort the target, it doesn't change anything at all. Change that trajectory, move to a different trajectory, it's exactly the same. Not only do I not notice a difference, I literally do not notice a difference. These two are still distinguishable. And even if I switch to another target, I could say, yeah, I can see a threefold symmetric target has a different category. They're classifiable. So I'll end with the fact that this actually works pretty well. I've not, at least in theory, I've not finished yet. This is the next step to actually start to compute these categories from laboratory data. It should actually be straightforward given the fact that the persistent homology has something to do with the factorizations that are involved. In fact, I might be able to do a little better. I might be able to use the famous Seifert-Van Kampen theorem to actually compute directly the whole set of factorizations. That might be possible. Well, that's pretty cool. And more to come. Thank you.
So we have time for questions.